different university with a red logo and stuff written on in Latin. So I want to talk about boundary conditions that we implemented specifically for running atmospheric boundary layers and wind farm simulations, and also talk a bit about the turbulence models. I'll try to keep it kind of short because it's been a couple of days. So yes, I think in general the setup that is commonly agreed upon in the wind energy community is kind of the best for running wind farms is that you have a precursor generation precursor simulation where you simulate an empty atmospheric boundary layer and you spin it up so that you generate kind of good turbulence and realistic inflow conditions, and then you feed that as the inflow to a successor simulation where you then actually have the wind farm, and then this is where you generate your results. And we do that because to generate good quality turbulence, we need to run the precursor simulations often for 24 hours of simulated time, and we have to do this in a periodic simulation. So the precursor, as I said, is biperiodic, and actually often we introduce a lateral shift in the stream direction, so that we don't. Because in the boundary layer you have these very long streaky structures, and if they kind of bite into their own tail, they keep feeding and feeding and feeding, and then you have a very characteristic pattern of high and low velocity streaks. And then you might, on average, have the proper, hub height velocity. But if you then look into the flow field, you will see these streaks, and then you have to start. You can start from scratch again because what you did was wrong. And so at the bottom we have a wall shear stress from a Wallmodel, and that we want to we want to implement that, and then at the top boundary we usually use a slip boundary condition, and then in the successor we generate the inflow, so it's not periodic anymore in the streamwise direction, but only in the lateral direction. So we want to generate the inflow from the precursor, and then the bottom and the top are the same as in the precursor flow, and then the outflow has to be some sort of non-reflecting outflow, so it just has to go somewhere. There's a question, yes?
Yeah, already, yes. When we have a lateral shift, does this mean that there is a bias in the flow, or do we misalign the periodic boundary?
Yes, you misalign it basically, yeah. Yes. Because that's why it also has to be periodic in the lateral direction, because then you're kind of allowed to do it, right? So yeah, you just introduce if you're in our coordinate system is usually y is the lateral direction and then z is up, and so if you just step a little bit to the left when you go out of the domain before you go back into the domain, so to speak, nothing really changes.
You shift. Yeah. Okay. Good.
Yeah.
Do you do random, or is it the same shift?
You have to. I will go through how we not how we implemented it, but how we use it, and you have to set it. And so I think the rough guideline that we always use is that it should be 1.5 times boundary layer height. But it's something you have to play with maybe. But yeah, you kind of have to run the precursor, and you will see did it work or did it not work. So do we get these streaks, or do we not get these streaks? Yes?
Doesn't this introduce like discontinuities at the inlet?
No, because it's periodic in the lateral direction as well. So if you think about each being like a brick, each simulation, then the simulation comes again. You just shift the brick, the row next to each other.
Yes, but the previous inflow from the previous time step versus the shifted version in the current time step, they come from different lateral positions.
No, they come from the same lateral position.
I thought at each time step we do a shift.
No. It's you set the shift once in the beginning, and then this is the kind of the topology of the grid and then you don't change it during the simulation. It's just, it's once. It's really just to avoid, it's kind of it's like, you kind of double the length of the simulation domain for these long structures. You get it? You understand? Or even more, actually. Yeah. Yes.
Can you draw it?
I can draw it, but that's not going to be on the recording. Can I draw on the... Ah, yes. There's a whiteboard here. Okay, so can I use this?
Yes.
Okay, so let's say this is the top view of our precursor, and then it's the same. Like numerically, it's the same because but we basically, this is the second time. So the outflow, let's say the outflow from here goes back at this position.
Yes.
And that's it. Instead of, normally the outflow would go back at this position. But we just put it back here.
So,
and that's it.
so
Yes.
basically on the picture that you have here, just have like
Exactly. Yeah. So it's really, yeah. So in the end, it's like if the domain was not like this, but it was like this and then like this, right?
Yeah, and this
that way, if you have a long structure, then if you set it up in the normal way, if you have a long structure that is like this long, it would start biting its own tail here and then reinforce itself, and then you are in trouble. But if you do it like this, the structure can be this long without ever touching itself, and that avoids this kind of self-reinforcing areas of high and low velocity. Yes.
Do you know why? I mean, like you explained a bit like why this could happen, but it's like your hypothesis, or is it like you are?
No, this is general knowledge. In 2016, there's been papers and papers. If you don't do this in your simulation, you will run into issues.
But you say something about usually we split up just half. So,
okay, yeah. You just do.
Something about boundary layer height, but
I think it was Muntas.
Because you don't have a boundary layer in this case, right? Like a height of the boundary layer.
Sorry?
You don't have a boundary layer height in your simulation here, right?
I mean, we have the height of the domain
Yeah.
as the boundary layer height. Yeah. You have to set it to something. I think it's just in the Muntas paper. I think we discussed this a lot. I think he recommended that it must be kind of wider than these structures are wide, and I think the widest they can be is roughly one boundary layer height.
Yeah, okay.
That is all. So yeah, we only set this up once. This was a bit of coding work, but after that, you don't have to do it, and it's it doesn't affect the running of the simulation anymore. It's just that you just change where the neighbor points to, basically. Yes.
Last question for slide 1. Do you have tried with some synthetic turbulence generators?
We can also, the precursor, we wrote it in a way that it can take any kind of velocity data. So it can also be synthetic turbulence. So I actually used it recently for like a MAN turbulence box. But that of course comes with other issues.
When you set the velocity field, do you also set the non-equilibrium part from that, or you just set the velocity?
We use, actually what, I will go through it later on.
Yeah, okay.
Okay, so this is the general setup that we want to simulate, and now we have to make it happen in LBM. So we start at the bottom. So we have to implement a Wallmodel, any kind of Wallmodel, and then we have to we want to compute that often the output of a Wallmodel. It can be a shear stress. Of course, it can also be something else, but we think shear stress works the best. And then we kind of have to set that shear stress. And then, you have the Wallmodel that is not LBM related, basically. That's classic Navier-Stokes. And then the question is, how do you impose a shear stress in LBM? And so the model that we are using, there's a couple models out there. I think consensus of what is really good is not that well established yet. But there was like 2021, there were like 3 models proposed. And we proposed this one and we stuck with that one because we think it works best. So it's this called inverse momentum exchange method that Henrik Asmuth presented in 2021. And the idea is that you compute a wall velocity in the bounce back scheme. So we build upon the bounce back scheme such that the force on the node due to the wall equals that force that we compute from the wall shear stress from a wall model. I go through it in a second. So this is the LBM bit, and then we have to compute a wall shear stress, and then we could use any kind of wall model, but in wind energy we usually use, well, we call it Monin-Overkopf similarity theory, but in the neutral case it's really just a log law. And then we use what's called the Gertzbach-Schumann approach to compute a friction velocity, and then from that a wall shear stress. So what you do is you have a so-called exchange location in the domain somewhere. This is kind of or a reference point where you measure the velocity, and then from that, that's the velocity in the domain, and then from that you compute the wall shear stress. But it's turned out that it's beneficial, or Monin-Overkopf theory only works on the averages. So what you do is you have to average this velocity somehow, and we do a pointwise temporal averaging of the velocity at the exchange location. But then you have to scale it to the instantaneous velocity close to the wall. And this is this Gertzbach-Schumann approach. Been around for, I think 30 years. So that's just some of the details. Yes?
What you say it turned out it was better to do the average time? What happens if you don't do it?
If you don't average at all, then you have to ask Henrik. I think if you don't average at all, so there is this, you have this, what's it called? The velocity mismatch, log layer mismatch of at the first node of the wall, and this temporal averaging reduces the log layer mismatch. Okay. So the theory is, in general, you have to decouple the computation of the wall shear stress from the first node, from the instantaneous velocity at the first node somehow. And there you can do it by spatial averaging, or by temporal averaging, or also by not putting the exchange location also at the first node. And we just combined 2 approaches with we picked the second node. I think this comes from the Palm people. I think they introduced this, that you use the second node and not the first node. And then there was other people that said, well, you can also do temporal averaging, and since it's basically for free, we just do this as well. We don't want to do spatial averaging because it's more complicated. And also, we always dream of generalizing this to complex terrain, and then this also becomes more complicated, right? So this is the general idea. This is the math bit of today. I think compared to the other days, it's definitely digestible. So the idea is that we compute the total momentum exchange between the node and the wall. And so in LBM you can, as Marty mentioned the other days, you can, because the populations are momentum, each population has a certain amount of momentum, and then if you take the population that went into the wall, and then it comes back from the wall after the bounce back, and if you you compute the difference, but if you then include the directional information, then you actually sum them up. There's a simplification already applied here. Then you can compute the force that the node exchanges with the wall. And the idea of the inverse momentum exchange is that this force should be the force that we compute from the wall shear stress. So there's also other approaches where they do it a bit simpler. They just say, well, the wall shear stress times the area is the force, and then they just impose like a drag force on the first node. Kind of similar idea. I think ours is a little bit more valid because we actually place the force at the ground instead of the first node, but yes. So you say, okay, the total force needs to be the force that we get from the Wallmodel. And then we split this, the force exchanged from the node into two components. We call it the fluid component and the wall velocity component. So if you do like the general, if you look into the general bounce back scheme, you always have the population kind of leaving the domain, and then you have the one that's kind of coming back from the bounce back. So these are what we call the fluid portion, and then you have a momentum added from the wall velocity. And now the idea is that we tune this wall velocity in such a way that, because we can choose the wall velocity, we choose the wall velocity so that the total force matches what we want to have. So the algorithm is actually kind of simple. So you compute a wall shear stress from a Wallmodel. Can be anything, and the moment it's only Monin-Orbakov similarity for neutral cases. And then you compute the fluid, the momentum exchange from just the fluid without or from a resting wall, let's say. And then you compute kind of what is missing, right? The force that we are missing due to to match the fluid velocity and the force, the fluid force and the force that we want from the Wallmodel. This gives us this wall velocity force. So now we have to go from this to this in the third step. So we have to invert this this equation, and
without the minus. ds squared minus m.
oh, there's a double dot
Double dot.
that doesn't belong there. So this is not easy to solve in general, and for specific cases you can solve it. Specifically for straight walls, it actually is quite simple. And we have implemented this for one of the straight walls, namely when it's the bottom wall. So you can only use it at this boundary at the moment. But if someone has time and wants to do this, we'd be very happy if you could generalize it. We are quite sure you can generalize it for most cases, but not all cases, but it's work. So now you have a wall velocity, and then you just compute the additional, basically compute this bit of, this is the added momentum per population due to the wall velocity, and then you just add that to the bounce back population that you had, and you have implemented a shear stress, or something in that direction, at least. Yes?
So if I understand it correctly, then if there is some friction on the wall due to, let's say you have a high resolution, so that you actually have some friction on the wall from below, but you're missing something, maybe even if it's too much. But you basically say it's different from what we wanted to, so we put a contribution.
Such that it's the one that we want.
Okay, that's very clever, I think.
Clever guy.
The way we do it is that we first subtract any contribution that might be from if we have a high resolution model, and then we add so that we have only the wall contribution. We do it this way. If there is something, you just add less, or as I understand.
Yeah, it automatically matches that. So the results for like an empty boundary layer, they are pretty good. They are better than most others, I would argue.
I think the nice thing with this really is that what you definitely see from outside always. I mean, if you just look at the very, very big picture, is the momentum exchange between the fluid and the solid. So this is this is unquestionable. And now actually you know what momentum is flowing into the wall, and you just adjust the momentum that is flowing out of the wall such that you get this particular thing. So once you know what friction you have, yeah. So how much momentum you want to exchange, then this becomes very, very simple.
Mm.
And I really think that this is a very good idea, and one that can be, that's very compatible with lattice Boltzmann, actually. Yeah.
After having reviewed also the others, I think this is the most LBM, one of the most LBM intrinsic.
Yeah.
And it is independent also of the collision operator. And you don't need an omega near the wall, which because we use turbulence models also, so we're going to talk about this later on. So the whole question of omega near the wall, the relaxation frequency near the wall, is a bit difficult, I would argue.
Yeah.
So this is absolutely independent. We never touched viscosity in this entire model. We don't need it.
Actually, we are using some of the most advantageous features of lattice Boltzmann, namely that it always deals with the flux density tensor. Yeah. So that this question, so how do I actually compute friction in the Navier-Stokes equation, where I have to integrate the pressure and the stress, so together, and this is here not necessary.
Yeah. So you avoid a lot of the nasty other nastinesses of other approaches. So
one last question then. You say the wall velocity.
Mm-hmm.
So is it to be? How do I interpret the wall velocity?
Yes.
Okay.
I call it a fictitious wall velocity, but you can interpret it basically like a slip, like a partial slip.
Yeah, okay.
I think that is one interpretation. Okay,
I think what we could say about this is just, I would actually say this is just a random interpretation that you put onto it, yeah, because you can always translate these boundary conditions into each other. Yeah, so actually you could also define this as what's called the anti-bounce back loop, because this is actually it's a little bit more like an anti-bounce back. So you squeezed this a little bit further by making it in a bounce back scheme. But I mean you can, because you can adjust any input by a specific velocity, by setting a specific velocity there. Yeah, so that would give you any input. So what really matters is that you get the outgoing, the incoming population, yeah, given the outgoing and the momentum defect, so to speak. Yeah. So what amount? So what it actually, the only question here is really how much momentum is flowing out of the domain. That's actually the only question. Yeah? And now you can translate this into a velocity such that you can put this velocity in your standard bounce back boundary condition. But this is only transforming one boundary condition into another domain. Actually, this velocity is not really of importance.
Yeah.
Yeah,
and I have the feeling there is also some simplifications doable of that algorithm, but I don't. It's my feeling.
There are some people who because you have also it's a logarithmic profile you try to resolve, and the resolution maybe don't allow that. And then some people argue that they adjust kind of the boundary, the Wallmodel such that instead of having a linear eddy viscosity, they have a constant in the very close to the edge. It's kind of also giving rise to a kind of slip wall also.
Yeah.
Which improves in there. This is a Japanese paper from Precurser like method. Not ABM.
All right. So this is the inverse momentum exchange method. And I think this is, yeah, at the moment kind of an exclusive of virtual fluids. So the next thing is the precursor. And this, I don't think anyone else has implemented in any other LBM solver. So the precursor inflow, we have to first generate the precursor data, and then we have to impose the precursor inflow. And there's actually two ways we can do this. We can use macroscopic quantities. You know, we compute velocities and sample velocities and feed the velocities back as a velocity boundary condition. And then actually what we do here is that we just use the normal velocity boundary condition and impose. So we have we use the same functions, but it's a separate boundary condition. Or you can actually just record the distribution, the populations, and feed back the populations that you're missing. And so the velocities, of course, is first of all more interpretable, which is always nice, and also is less data because you need 4 quantities per node per time step. Whereas for populations, you need 9 populations, right? Because you're missing 9 populations that are streaming into the domain from the outside. So it's much more data. But we found that since the smallest time step in LBM is much smaller than actually the smallest features in the flow, we don't need to, for good results, we don't need to record and feedback every time step, but we can do a linear interpolation between 2 time steps. So we record one set of population at t, and then, you know, t plus 10, and then we do a linear interpolation in between. And we see that roughly, if you take every 10th time step, we don't start seeing a difference. If you go beyond that, then you start seeing a difference, but that cuts down the data that we need by 10. So it is the data that we have to write out during the simulation, and also, and this is actually the bigger problem for us usually, just the data on the disk, because these things get huge. You know, because you have a large domain, and so this actually, I think this was kind of the point where it actually became feasible, because before that, yeah, my disk was always just full on my computer.
Did you try only linear interpolation, or did you try?
I only tried linear interpolation, and it works.
Yeah, no,
fair enough.
I was thinking of a way if you have a higher order interpolation that you could use less.
Maybe even less.
points.
That is probably even true. Someone should implement that. So.
Use the precursor for a UAV, there's no need to output velocity, right? It's only if you if I wanted to use it in another solver.
Yeah, exactly. If you want to use it in another solver, of course. And as I said before, like you can also make a precursor from synthetic turbulence. So you generate a man box, and then of course the output of that is velocities, and then we just wrote it from the beginning in that way that you can just use that, that we can just use that as well. You just have to provide it in a VTK data, but I mean, that's doable. You just, yeah, get any of the man box generators out there, and then you just take the data and open it in ParaView and then put it in a normal VTK. Actually, I put this in because I'm quite proud of this bit. I think this is my computer science contribution. So we actually can have 2 levels of parallelization when we're working with the GPU and the disk, because we have the huge precursor data. Actually, we do have to split it into multiple files usually, because otherwise they just become too large, because this is easily multiple gigabytes. And just the VTK format has a limit, and then it doesn't, you're not allowed to put bigger data than a certain amount. So, you know, let's say we have these 3 precursor files, each with 100 time steps. And then what we do is we load one from disk concurrently while we're going through the one. So in the beginning, we load one from disk, and then we immediately start concurrently loading the next one from disk into RAM, because you always have to go from disk to RAM, and then we can go to the GPU RAM, the VRAM. And so we always have the one that we currently need in the RAM, and then we have two time steps of the precursor data on the GPU, because on the GPU we could of course push the entire precursor into the GPU RAM as well, but we don't want to do that because we have very limited space there, because we want to fill that with simulation data, right? So we only have the last times the time step, the two time steps that we need for interpolation, for linear interpolation right now. So the boundary condition actually takes very, very little space on the GPU. And then we're concurrently loading already the next one that we will need. And that way, we never have to wait. We also do this, we do like memory transfer hiding. So we never have to wait for it. And that actually makes this the fastest boundary condition in LBM besides the periodic boundary condition. Because we don't, if we use the precursor, if we use the population precursor, we don't actually have to do any computations. Or we do like linear interpolation of the data, but it's very, very, very easy compared to anything else. We just write 9 populations from this kind of buffer into the boundary, into the right node. So it's actually very easy, and because we have these two processors, right? We have the CPU and the GPU. We can actually, if we use them smartly, we can do more things at the same time.
And how much faster? If this is something you developed because you saw it was slower, maybe?
Because we didn't want to wait because otherwise you need to, if you do it, I mean reading the precursor data from the disk to RAM takes quite a lot of time because it's a large file.
Yeah.
And then also if you had to wait every single time and so on, it would just be slow.
You started out with that and then you did this later, or?
I think we kind of immediately went to that. So yeah, don't look at it though; it's very ugly. It's really it's the fastest bit of code I wrote, but it's also the most horrendous. But it works. All right, so that's kind of the boundary conditions. Last bit that we implemented are turbulence models. So as also previously discussed, we found that we can't solely rely on the cumulant and its implicit damping for running LBL flows because they're just too coarse. So we need additional viscosity because otherwise we get a detachment of the flow and a shock wave starts to build up. And that's of course that's not how where we have gusts, of course, but it's not the same. So we wanted to have an explicit turbulence model also, of course, because it's then also better comparable to the rest of the wind energy community because they're all using turbulence models. So what we typically do is that we turn off the implicit damping. So we set the limiter to a very high value. And then we only use the explicit turbulence, the explicit LES from the explicit subgrid scale effect from the turbulence models. This works and is stable unless you use refinement. If you use refinement, you have to set some value of the limiter that's a little bit below 1. So the way you implement it, yes?
Can we set like a level of a liter in the refinement like differently than in those?
No, it's
No, because the refinement does not. I mean, I have kind of a little bit an idea where this may come from. Yeah, but that's my own hypothesis. So in the refinement, we only recover the up to the second order moments, and the ones that are limited are the non-equilibrium third order cumulants. And they are not actually set in this in the interpolation after the interpolation. So they are now they are in principle inconsistent, but the point is that they are this so-called ghost moments usually that to second order in asymptotic analysis they don't count. They only count if you go to this higher order. And so far we decided that in the grids interface, this is too complicated. I mean, you're losing information in other ways too. So we cannot do this. Maybe we can do, but it has been too complicated to actually try to do it, to set the interpolation to higher precision than second order. Yeah, and therefore these super convergence things in the third order cumulants, they are not consistently initialized at the interface, and this is where the limiter is acting. So inconsistent, by the way, means we're setting them to 0. So we are not setting them to any stupid value. We are setting them to 0. The problem is from the nodes next to them don't have 0. Yeah. So then there is a jump. And I guess what you observe, so this is my hypothesis that I make up on the spot, is related to this, that there is a jump in the non-equilibrium third order cumulants that are usually used to get this superconvergence.
So that's why we're here, to understand this. Because I had no idea. I know how to fix it though. You turn on the limiter.
So you always have to think practical, yeah?
Yeah.
Always try.
Well, so yes, so we computed turbulence viscosity, and then we added to the to the molecular velocity key, which is negligible compared, and then we recompute the relaxation rate, the omega. What is nice is that in the cumulant kernel, we compute all entries of the stress tensor. Anyways, if you use the K17. So if your model only depends on the entries in the stress tensor, so not the velocity gradient tensor, but only the stress tensor, then we can do this at virtually no cost. Because we already have these derivatives. Or in some cases, these combination of derivatives. If you have a model that requires that requires the full velocity gradient tensor, so du by dy or dy by dx, then you have to do it in a separate kernel, because then you have to make sure that you've done all the collision and updated all the velocities, and then you can do a finite difference tensor and compute the velocity gradients. So there's this one little inconsistency here also, that when you're computing the stress tensor from the cumulants, you're actually using omega. So you're using omega to compute the stresses, to compute omega, to compute the stresses, to compute omega. So actually, Martin suggested we should iterate there, and we said yes, but we're just going to iterate in time. So we just use the one from last time step. And since the differences are, time step small, we think it's fine. So we have implemented actually 3 turbulence models. We start with the classical Smagorinsky model, which is nice because it only depends on the stress tensor. So we can actually implement it directly in the kernel, and actually with the Smagorinsky specifically, you can actually avoid this inconsistency by inverting something. But Smagorinsky generally is not a good turbulence model. I think this has been established. So then we actually didn't jump to the second one, but we actually, for some reason, jumped to the third one, the anisotropic minimum dissipation model, which is it's a very good model. It turns off near the wall, does all the things you want from a good turbulence model, but it doesn't only depend on the stress tensor, but you need to compute the whole velocity gradient. So it's another kernel. It takes some time. It's also just not so good with at the walls and stuff. So it's but the anisotropic minimum dissipation, the anisotropic comes from that it's made for anisotropic grids. But we don't have anisotropic grids. We have isotropic grids. So we actually went back to the original model, which is called the QR model. And the Q stands for the second invariant of the stress tensor, and the R is the third invariant of the stress tensor. So it only uses the stress tensor, and it's a really good model, so we use this. So we actually compute this in the kernel, so it comes at no additional cost. We have a turbulence viscosity, and I think I'm happy. So I think that's it with the theory, and then I was just going to show you how you can find this stuff. Are there any questions? No? All right. So
Have all come on the way.
is that a good sign or is it a bad sign? I don't know. All right. If I now go over here, yes, it's gonna work. All right. So I'm now in larger. Yeah? Can the last row read this? Okay. Yeah. Those are the easiest. Thank you.
Yeah, it's easy.
Or not. You never know.
So we have like two nodes near the wall, right? Before the boundary condition.
Yes.
It's like on top of each other. And we expect this to be a log law.
Yes.
If you have the velocity at the second one, you can calculate the velocity at the first one, you just apply then a slip. Does this work?
No. Because, I mean, how do you set the velocity? You can set the equilibrium from the velocity, but that's not going to be good. You also need you need a viscosity to do that. It's not going to be good. You need a viscosity to do that.
No, I mean like I do a velocity bounce back at the one near the wall, based on what I calculated from log law.
But the velocity is 0. And your stress are not going to...
Well, that's the thing.
But you have the problem is that you have a very high gradient basically between the wall and the node. And that is the problem. You can't set the velocity, which the solver basically doesn't see, right? You have very high viscosity, like a lot of very small scale turbulence near the wall. And actually between the wall and the first node, you have so much turbulence that affects the flow that you don't see in the simulation, but we know that's the result we want to see.
You have like a delta x of how many meters?
5.
Okay. And then if you measure it, it's still, you are saying, is it going to be a log law? Like if you have like 2 measurement points and...
Yeah, it's going to...
And then you think...
I mean, how good Monobukov is.
Wait.
It's just
The
a practical
that's
thing.
the average velocity that has
Yeah.
a log.
Yeah.
Yeah.
Yeah, exactly.
It's
So
not even clear how, how from a practical point you're doing this. Because you have to set the instantaneous velocity such that you get the right.
But if I have the average, I can...
it's going to be not so good of a result as if you do it like this.
Okay.
Also, you don't know how far the log law is valid. Like, it's not valid throughout the whole domain.
That's why I asked it, because I was like, anyway, this is like, by the way, it's like a matter of which one is more accurate or less wrong. So like.
Our way is much less wrong.
Okay.
What you're describing is a bit similar to the first way that a Wallmodel was implemented in LBM, which is the Malas-Pinaches post from 2014. The results are...
They reconstruct the entire population on the wall given. Yes.
So there are models that are similar to that. I think for our case, ours works better. Yes. Okay, so many of the things I just talked about are implemented in the atmospheric boundary layer .cpp app. Now we're back on the GPU. In case, we're not entirely on the GPU, of course, but this is the GPU version of virtual fluids. So here we also start with the header. And we set a roughness length for the Molin-Obokov theory, or for the log law. And here you also have this periodic shift. So this is the value of the lateral shifting of the boundary condition. So this is going to go in y direction. And here you have to set a value. And already this app can both write and read a precursor. But of course you can, you have to run it once with write precursor, and you have to run it once with read precursor.
But the periodic shift, what is the unit there? Is it like in, so if I write half, is it
We'll see.
okay.
I honestly don't remember. It's either boundary layer heights, or domain heights, or absolute values in SI units. I'm honestly not sure. Yeah, we can read or write a precursor. Here you can also set if you want to use the distributions precursor, if you want to write the velocity precursor. So you can also do both. And then you will have a directory where you're going to write the precursor. And here you have this number of time step that you write the times every how many time steps are in between each write of the precursor. So this is also going to be your interpolation later on, right? So this is set to 10. We need quite a long spin-up time. I think now we use usually 10 hours for the spin-up time before we start recording the precursor. So, turbulence has to develop, and so on and so forth. And time step between read. And then here we set the velocity profile. So it's really just a log law. And then here we compute everything to LB units, and we usually use a pressure-driven. Well, we always use a pressure-driven boundary layer at the moment. So yeah, we set everything up. It's also already implemented for multi-GPUs. So if your domain is too large or your GPU too small, which one's which? We don't know. Then this already it works out of the box, more or less. So this is then here. Here you can also set refinement, but here we do this still by hand in this case. But actually now Virtual Fluids, the GPU version also contains like a wrapper, kind of like the helper classes that we saw yesterday, called the multiple grid builder facade, that makes all of this way easier. We just haven't used it in this app yet. That then, where you only have to specify where do you want to cut the domain into the so-called subdomains and distribute it on the GPUs, and then it's going to distribute it on the GPUs automatically. And then here we set the value of the periodic shift. So you have to give it in absolute units. So if you have 1 kilometer boundary layer height, then you will have to say 1,100 in the configuration file. So here we actually implemented this for all boundaries and in all directions, but you have to set the periodic shift on the x boundary in the y direction. That's why we named this function this. Yes, and then we come here. We set the pressure gradient, so it's it's a constant force in the entire domain. And here we have our initial conditions. So this is, if you remember, in the GPU version, it's done a little bit differently than in the CPU version, that you define a lambda function so an anonymous, or you can put any CPP C++ function as to generate the initial condition of the macroscopic quantities. And we have found that this very specific way of initializing it kind of triggers the generation of turbulence the fastest. We didn't come up with this, someone else came up with this, but this is what we find. So if you just initialize your domain with the log law, it's going to take a very, very long time. You're going to need a lot of spin-up time. And of course, LBM is fast, but you're still producing a lot of heat that you don't need to. So we find that this triggers it much quicker.
Is this divergence free?
This is divergence free, yes. It was developed for incompressible flows, incompressible solvers. I think they would not allow you to not do that. Yes?
There is no Coriolis.
No, pressure driven. No Coriolis.
As soon as you have that, then you don't need to have the periodic shift.
True. Yeah. I mean, I've been working on Coriolis force. The problem with Coriolis force is it's very small. And very small forces are not good. Because we actually think that they are too small and they kind of drown in the numerical precision. So we had to play around a bit with that. And I think we have found a solution, but it's not, no, I'm not going to record that. But we have found one. So this is how we initialize the domain if it's empty. If we are using the precursor inflow, then we initialize it then you can initialize it in a simpler way, right? Because you're going to get turbulence from the inflow. Here we still, as I said, we still do this by hand in this app. This is how you set up a multi-GPU topology, like how the different bits connect to each other. And importantly, you have to set, when you do this find communication indices, in one direction, you will have to say this do shift to true, which is that you apply this periodic shift on this specific boundary. But you must only do it in one, because if you do it in two, and in the back and in the forth, they cancel each other out, and then you have not shifted. That took me a long time to figure this out. Okay, so here we come finally to the precursor. So if we want to use the precursor inflow, and this is either not multi-GPU or it's the first subdomain. So we're gonna, this is the subdomain where we're gonna set the inflow. We have to first create the so-called file collection. So this is kind of a wrapper object for all the precursor files on the disk. And this is going to handle like all the disk communication. So we have to set a directory and then the prefix of the precursor. And then we have different, well, you could in theory have different file types. So if you want, if you have, for example, you're going to use the MUN turbulence generator from that's built into Hawk 2. That has a very specific file format. You could implement a new file format, and then this is kind of an abstraction from the precursor and the file format, how it's written on disk. So you could implement a different file type here, but as I said, at the moment it's only these VTKs that we also always use in virtual fluids. So you create the file collection, and then you have to set the precursor boundary condition. You have to tell it where, give it a file collection, and then how many time steps there are between each read of the precursor. And then you're going to run a precursor boundary inflow. So it looks like any other boundary condition, really. So this is when you already have if you have already generated the precursor data. this is, here you can set the stress boundary condition. So this is the IMM boundary condition. So we set it at the bottom wall. Here you have the sampling offset of the wall model. So this is the how many nodes, or the how many nodes of the wall you want to put your exchange location, and it starts counting at 1. So if you set this to 1, it will be the first node of the wall. If you set it to 2, it's the second node of the wall. It's not, because usually you start counting at 0, right? Well, if you use Fortran, then you don't, but in virtual fluids, you usually start counting at 0. But this is the second. And then we set all the other boundary conditions. Here we have to pick which one we're using. So for the precursor, here we have to tell it if it's going to be a distribution precursor or a velocity boundary condition or a velocity precursor, and then this naming is tells you which kind of velocity boundary condition we set. So these correspond to the normal velocity boundary conditions. And then the next thing, here we also have these planar average probes that I mentioned before. So they compute a planar average of the entire, so yeah, for each level in the entire domain. So they work very much in the same way like the other probes. You have to give it a bit of information about the simulation, an output path, so the directory where you're going to put the output, a prefix, all the time steps, and then which axis you want to have, which is the normal direction of the planes that you're going to average over. So in theory, it works for all cardinal directions. And then you can also online compute the temporal averages already, and I forget what the false is. And then also you can add. There is quite a lot of different. There are quite a lot of different quantities that you can statistics that you can compute. So you can, we usually we just say like all of them, but you can also set them individually. Planar average probe, add statistic, and then you have to pick a statistic, and that goes like this. So planar average probe, statistic, and then you can have the means, the covariances, so second order statistics, and then also the third and fourth order statistics. And then for all velocities and also concentration, if you have a concentration, and all the higher order, the third and fourth only like the auto variances, but the other ones also all the covariances. So you can do a lot of post processing. And then we also have the Wallmodel probe. So if you want to know something about what's happening at your Wallmodel, if you want to compute the friction velocity in your domain and so on and so forth, you can do that. So this computes always the average over all boundary nodes. And there I quite often use this time series output, which is, you write not a VTK file for a single point, and then you write a VTK file for every time step, but you write one large file with all the time step data in one file. So you just have a time series.
How is that actually written? Is that then written to the no, it's not virtual, the RAM that basically, or how? I mean, so are you writing at every time step then actually? And is that a performance problem? I mean, should you be careful how to choose things?
No, because it's just going to write like one line. It's not. I mean, it's the Wallmodel probe. It only takes the average of all the nodes. So it's only one. You're not going to write 10 points, but it's only like maybe 10 statistics, but only 1 point.
Yeah, it's more
so
write out an entire plane.
No, that you wouldn't do anything. So it's, yeah, I wouldn't say it's a performance problem. Actually, maybe it also buffers it on the RAM for a while and then only writes it onto the.
Oh, okay.
But I'm not entirely sure. And then I think the final thing we should talk about is how you use the precursor writer. So the precursor writer, because it doesn't actually do anything to the simulation, it's also what we call a sampler, right? It's just a probe, because it just produces output. So you have to give it which kind of precursor you want to write. So this is what's called the output variable. So it can either be the distributions or the velocities. And then you just generate this precursor writer object and add it to the simulation. And you just have to give it a plane in. So the precursor is kind of very limited in the way that it only allows you to. It only works on the inflow plane it's on the YZ or the MX plane in virtual fluids language. So the normal inflow plane. You can't put any of the other sites as a precursor at the moment. So the precursor writer is also targeted exactly for that. Yeah, that's I think it's kind of straightforward. So yeah, it works. It looks exactly like all the other probes. And then the last. So this is how you write the precursor, and then you feed it back into any kind of simulation with the precursor boundary condition, and then you have to create this file collection. And then with the turbulence models, you have to create this turbulence model factory, like I also mentioned when we talked about the actuator line app. And then actually it can just read the configuration file. And there you have these two specific keys called the turbulence model, and that has to be a string, and it has to be either non-Smagorinsky, QR, or AMD. And then you have to set the SGS constant. So if we don't use the limiter, we set the SGS constants to 1/3, because it's the recommended value for the QR model. And very heuristically, if we put on the limiter, we turn this one down a bit to 0.2. We have not really done a very thorough investigation of these two things, because they do affect each other, yes, this kind of works, but maybe there's better options even. Don't know. But you can also, you don't have to read it from the config file, you can also directly set it in the app with set turbulence model, and then I can either give it the string or exactly like this value of IBM, the turbulence model, and they are hidden here, and then it already pops up which turbulence models you have. So the QRs, Smagorinsky, and AMD, and also very recently we added the AMD for stratified flows, but the stratified bit is not there yet. The turbulence model is there already though. And yeah, that's kind of it. And if you wanted to turn this into a proper successor, you have to add a wind farm. But that, then you go into the actuator line app and copy those two lines, and then you have a setup. So yeah, that's it from my side. Are there any questions?